Okay, so I'm just gonna give you an explanation of how you can start from a Fourier series for a periodic function and then obtain the formula for the Fourier transform, which is a way of representing a function on the whole real line, which normally has to be decaying fast enough at infinity for it to be well defined, but how that naturally comes out as the limit of a Fourier series that you've already seen. Okay, so I'm assuming that you know what a Fourier series is, that you've seen that before, but once we start using Fourier transforms, we can kind of forget about Fourier series if you don't remember much about Fourier series. But the starting point, so going from a Fourier series to a Fourier transform, is that you have a periodic function f. So typically you might be used to working with real functions, real valued functions. But it's going to help if we actually think about everything being, all the functions being complex valued for what we go on to do. So it doesn't matter if you want to have a real valued function, that's fine as well. But just think about a function that's periodic, so it has period 2 pi. So that means that f of x plus 2 pi is equal to f of x for all x. So for all x in R. And then the basic thing that you would have learned if you studied Fourier series is that you can represent f by a Fourier series. Okay, as long as f is as long as f, you can integrate it. So what does that mean? Well, it means we can write f as a sum of sines and cosines. Okay, so if you, when you learned Fourier series before, you probably learned to write Fourier series like this. And the Fourier series are, okay. So these things, an and bn, are the Fourier coefficients. And then, okay, so the Fourier coefficients are given by an integral formula. Okay, and I'm not going to write down the integral formula, but what I'd like to point out is that it's something that perhaps you didn't study when you studied Fourier series. So using, oops, I'm sorry, I pressed something wrong there. Okay, so using the fact that that you can write cos and sine in terms of complex exponentials. So I've written e to the I nx in terms of cos nx and sine nx, or you can also write cos nx in terms of e to the I nx and e to the minus I nx. And similarly for sine nx, oops, I'm missing an n there. Okay. I guess if I want to be really careful, I should put brackets around the arguments here if you want to be really precise. Okay. So if you use this fact, you can also write f as complex Fourier series. So I mean, there's nothing really different here. Oh, sorry. Pull up. So what do I mean? Well, I just mean that you can replace this sum with coses and sines by a sum of complex exponentials. And the nice thing about that is that it's a kind of much neater formula to write, okay? So that's one reason why I think it's a superior way to write a Fourier series. But the other thing is that the formula for the coefficients oops. A little bit. So the formula for the Fourier coefficients is a lot simpler, I would say. The point is that there's just one formula. Whereas when you write it with coses and sines, you have to write the a ends and b ends. You have a separate formula for coses and sines. So if you work with this complex version, then you just have a nice, simple formula for the coefficients, which is you take f of x e to the minus I n x dx. Okay, so that's the formula. And before we carry on, I'd sort of like you to think about that as somehow two different ways of representing the same function. So you have this function f of x, and you can specify a formula in terms of x, but you can also think about this sequence of numbers Cn. And so if you know these numbers Cn, then that also means you know the function f of x, periodic function. So the way that I'd like to think about that is f is a function of x and c is a function of n, but n just takes discrete values, so 0 and plus or minus 1, plus or minus 2, and so on. So all the integer values. Okay, so now I kind of want to rescale the formula, and this is where I sometimes become unstuck doing this derivation. So you'll have to bear with me because I sometimes get the scaling wrong. But remember that we started off with a function that has period 2 pi, and that means that we have these exponentials which are basically e to the ix, and then all the sort of powers of integer powers of e to the ix, because e to the ix has period 2 pi with respect to x, and then any power, nth power of that, where n is an integer, will have the same period. So now, in order to do a kind of scaling, I want to think about if we had a function that has a different period, which I'm going to call 2L, and L is sort of for length. And I'd like to think about the fact that, here, when we had a period 2 pi, we integrated to find the Fourier coefficients on a symmetric interval from minus pi to pi. And so what I want to end up with is an integral that's going to go from minus L to L when I look at a function that has period 2L instead. Okay, so what I want to end up with is, let's say that so I want to consider a new function. I'm going to sort of abuse notation, which is going to have, so I'm still going to call it f, but I'm going to have the same period. Sorry, not with a different period, not the same period. So I'm using the same letter, but I want to have the period being 2L. Okay, so again, maybe I'll draw with a different color. Okay, so f of x plus 2L is f of x, all x in R. Okay. So now what I want to do is modify the formula. So I want to modify the formula for f. So I'm still going to write f as a Fourier series, but I'm going to have to scale. I'm going to have to scale various things. So, okay, for the main thing I'm going to have to scale is x. Okay, so how do I want to do that? Well, the point is that e to the ix and all the powers of that has period 2 pi. So if I want to get something with period 2L, then I'd better scale x by basically something like L over pi, I guess. So let's see. So let's see what happens. So what I'm going to do is I'm going to replace x in the formula for f is going to be, so here's the Fourier series. This is not looking so neat, so let me try and make it look a bit neater. Okay, so the point is that if I replace x in that formula, so in each of the exponentials that appear in this, so I'm talking about, oh my goodness, I don't know what happened there. think I'm still sharing the screen with you, but my my screen just popped out, so hopefully nothing happened. So what happens is the Fourier series for f is going to change now. So this formula, let's change the color. Okay, so I'm talking about, oops, I'm sorry. I've lost the screen that I was going on. Yeah. So sorry, I'm talking about the right-hand side of this formula up here. So what I want to do is rescale. So what that means is okay. So what I want to do, I want to replace x with pi x over L in each of these exponentials in here on the right-hand side. Okay, so let's go down and write down what the Fourier series is. So the Fourier series is, I'm going to sort of leave a bit of space to give myself room to maybe do some more scaling as well in a minute. Okay, so what I'll do is I'll leave a gap in the front because I want to change something possibly in a minute. So the point is I can, now again, I'll write the coefficients Cn. But now instead of I n x, I need to do I n pi x divided by L, okay? So now the point of this is that if you look at each of these exponentials of an imaginary quantity here, that's sitting here, if I replace x by 2x plus 2L, then that would shift, if you like, the L's will cancel, so that what that will do is shift the overall argument of the exponential by 2I pi times n. And if you shift an exponential by an integer multiple of 2 pi I, then it stays the same because e to the 2 pi I is 1. Okay. So the point, so this is what I'm saying. Sorry, let's do that in a different color. So what I'm saying is that if I take e to the I n pi, and then I shift x by 2L, right, inside. So each of these exponentials here, I've shifted x by 2L. And what happens to that? Well, that's equal to e to the I n pi x over L. And then I've added on 2L over L. There's a 2L over L here, so that gives me 2. So it gives me 2I pi times n, but e to the 2 pi I is equal to 1. So e to the 2 pi I times an integer n is just equal to 1. So this is equal to I n pi x over L, right? So that's period 2L. All right, so that's going to be my new Fourier series for this function with period 2L. And now what's going to be the formula for the Fourier coefficients? Okay, so this is where I'm afraid I'm probably going to have have to fiddle with the formulae a little bit again to cheat slightly. Well, not really cheat, but just to fix my scaling. Okay, so then the point is the Fourier coefficients. If you look at so the formula for Cn is going to become okay, so now I think I know I know what I want to do here. Okay, I'm sorry. So I'm gonna write down the formula, and then I'm gonna do some messing around with it. Okay, so I hope you don't mind if I do that. So okay, the formula that we had a 1/2 pi, and before we had this formula for Cn had 1/2 pi, and then an integral from minus pi to pi. So when we do this scaling, we get an integral from minus L to L, and we have f of x, and then now we're going to need to have e to the minus in pi x over L dx. Okay, and I've got to make sure that this gives the right answer for the coefficient. So if this is going to work, then I've got to integrate over. If I integrate over minus L to L, then I've got to put in a factor of 1/2L, whereas before we had 1/2 pi. So it's like 1 over the period is what appears in this integral here, if you do it like, if you scale it like this. Okay. Now, what I'm going to do now is put in some, do some kind of messing around with this formula slightly. So let me explain what I'm going to do. This formula is still correct. Suppose that I wanted to redefine all of the Fourier coefficients by just multiplying them by a constant, let's say, okay, so I'll use a different color for it. Okay, so this might look a bit kind of artificial, but it'll make life helpful. Okay, so I've sort of used red already, so I think I should use a different color, maybe some kind of pink color, maybe this. Okay, so I'm just going to put a constant. I'm going to call it alpha, and there's no particular reason. So what I've done in the top formula is I've replaced Cn by alpha Cn. Okay, so everywhere that Cn appears before, it's really become alpha Cn. So that means that this formula for the Fourier coefficients is still kind of good, but but I've just had to replace Cn by alpha Cn. So alpha is some constant. Okay. So this is sort of maybe a good way to avoid making any mistakes. Okay. So now I want to think about what happens with this periodic function. So I've got the Fourier series, and I've got the Fourier coefficients, which are given by this integral. And now what I want to think about is imagine a kind of limit where I look at letting the period, so 2L, letting the period of this function, let it get infinitely large. So the quantity L, I can take L to infinity. Okay. So what we're going to do is now consider the limit when L goes to infinity. So in particular, the period, which is 2L, is also going to go to infinity, goes to infinity. That's really the important thing. So the point is, you can have a function, you can, for a periodic function, you can just define a function on a finite interval in X, and then you can extend that to the whole real line by just repeating the same values that appears in one block of length 2L. So just keep repeating it. That gives you a periodic function once you've specified it on the sort of region of width 2L, then you know the function everywhere. But what about if we wanted to think about a function that is not periodic? Well, we can't define a Fourier series for it if it's not periodic. But we could think about defining some other representation for it, which is also involves something like a limit of a Fourier series. So the way that we do that is if we think about letting the period go to infinity, then we have a function now on the whole real axis from minus infinity to plus infinity. And what happens when we do that? Well, you can see that we've got an integral with respect to X, which gives us Fourier coefficients. But what about these exponentials? Well, it's kind of a problem, I suppose, because okay, where are we? So we have like our function of X. Let's think of it as a real function. Think about its graph and whatever it's doing. And let's say we've specified it, however, in this region from, okay, well, maybe I should. So I'm not doing a very neat picture, but suppose this is minus L and this is plus L. Yeah, I might sort of fix it in a certain way, which you'll see in a minute why I'm doing this, but okay, I'm sorry. I'm going to start again with my graph because it's not very successful. Okay, so I actually want to think about a function that goes to 0 at the endpoints. You'll see why. And then I want to think about kind of stretching out. Yeah, so I mean, you can think of X should really be stretching, or you can think about just L stretching. There's different ways to think about it. So there's your function, and then with period to L. Okay. And then the Fourier series, so for what you have is some values. So let's draw, okay, let's draw another graph. This is a kind of a strange graph maybe to draw, but we have Cn. So I don't really mind, well, okay, this is 0, 1, 2, 3, -1, -2. Okay, so I don't know what the values are, but for each n, there's some value of Cn. And okay, really, they might be complex numbers as well, so I wouldn't be able to plot them on a graph like this, but so these are the coefficients. Okay. So what happens in the limit I want to define a new quantity, which is going to be n pi over L, which is going to be the wave number. Well, okay, it's a little bit, this is where it gets a bit harder to talk about exactly what this means in the limit. But as you take the limit, okay, so rather what I really want to say is consider this quantity's k. Which is given by n pi over L. Now, the problem with what I've said is if you just consider, sorry, my screen has done something weird. Let me try and get rid of that. There we are. If you consider this k when L goes to infinity, then it doesn't really seem to make sense because it just goes to 0, right? If n is a fixed number, then n pi over L goes to 0. But what I want you to do is sort of think about the new graph that you're going to get. So let's think about the new f that we've got. So again, I'm not really going to try and draw it properly, but let's just say, okay, it's got some wiggles. I'm not really drawing like an accurate picture, but something like that. But it's really meant to be defined. Okay, it doesn't look like the same function really, but it's a similar function, and it's got lots of wiggles, and but it's defined on the whole x-axis. So that's like in x, this is x space. I'll call this x space. So it's like x is imagining space is one-dimensional. And we're thinking about a function defined on x space. And again, I've drawn a real function, but for what I started with, we could think about f also taking complex values, not just real values, but then I wouldn't be able to draw the picture. And now I want to think about what happens in k space. Okay. And rather than say that we've taken the limit already, I want to think about when L is very large and what would it look like if we plotted values on the k-axis. Okay, well, values of Cn, but so the point is that when n equals naught, you would have k is naught. When n equals 1, you would have pi over L. When n equals 2, you would have 2 pi over L. When n equals 3, you'd have 3 pi over L, and so on. And then when n equals minus 1, you've got minus pi over L. N equals minus 2, you've got minus 2 pi over L. Okay, so this is a kind of a lattice or one-dimensional lattice, just regularly spaced points on the k-axis. And we can fix for each of those points, we can fix a value for each n, we can fix Cn. But now what I want to do is look at the spacing. So the same, so I'm going to call this delta k. And then this is delta k, and so on. This is delta k. Okay, so the spacing so the distance between the points here is pi over L. Okay. So now if you imagine how this would work, okay, you've got your lattice spacing. And so what happens when L goes to infinity is that delta k tends to 0. Okay, so the distance between all those points gets smaller and smaller, goes to 0. And so, you know, n is still going out to infinity. So as long as you're letting n go out to infinity, then you're actually going to fill up the whole k-axis densely with the points. The lattice points are going to join up finally and fill up the whole k-axis. So the idea is that should remind you of something that you saw in analysis when you divide up the axis into regular intervals. So, for example, if you did any of the integration rules like the trapezium rule or Simpson's rule, any of those approximations for integrals, and the idea is that when you're trying to estimate the area under a graph, you divide it up into some kind of shapes and then approximate it. And then as you take the gaps between your, points on the axis smaller and smaller, then you approximate your integral closer and closer. And so if you studied the theory of integration in analysis, then this kind of, this is a way to get what's called the Riemann integral. Okay, so the idea is if you have a sum over lattice points, and then you let the lattice points get closer and closer, what you end up with is an integral. So if we just go back up here to the previous page for a minute, then we've got two things. We've got an integral for the Fourier coefficients, and we've also got a sum for f, which is a Fourier series. And so the idea is, oh dear, yeah, no, sorry, I'm saying oh dear. But the idea is that, the idea is that we want to get that sum to become an integral in the limit when L goes to infinity. So what happens, so you have to kind of remember that sum that I wrote up there above. So, so how can we write, sorry, oops, I'm flipping through too much. So now the point is that the Fourier series is f of x is the sum. I'm sticking this constant alpha inside, and this is a sum that goes from minus infinity to infinity, and then I can write this as e to the I kx. Okay, and what I want to think about this is to think about this as a Riemann sum of a function. So Cn is a function of n, but I really want to replace that by a function of k now. So think of, if I know k, then I know n, and vice versa for a fixed value of the period 2L. But I want to think of this as a Riemann sum. So this is like, I guess I should sort of put some kind of approximately equal to, and then I'm going to say a sum over k values. So we've got a discrete set of values, and I want to think that of as being a sum of a function f of, so I'm going to call this function f hat of k times e to the I k x times delta k, and I'm going to put 1 over 2 pi in front. Okay, so let me make, this is, there's a choice of, why I say this is sort of, it's easy to for me to mess this up, is that there's a choice of scaling when you define Fourier series. And here I want to have a nice formula. Well, I want to choose the scaling so that I get I guess I don't really even need to put approximately equals. I can actually just make this equals. So k is n pi over L, and I just want to say that this is f hat of k on 2 pi times e to the I kx times delta k. So this is, what have we done? We have identified so alpha Cn is the coefficient of e to the ikx, and k is n pi over L. And then we've taken, we've called this 1 over 2 pi f hat of k times delta k, okay, where, so let's draw it in red to emphasize it. So delta k is pi over L, that's the lattice spacing, and k is n pi over L. Okay. So, I mean, there's different ways to think about this. You could, again, when you're thinking about approximating a function, and also thinking about whether this, sum is convergent, you might want to keep everything on a finite interval. And, well, so far everything is on a finite interval between minus L and L, but you might want to sort of control the endpoints of your region more precisely as well than I'm being. So, okay, the point is that if you know Cn, which is the coefficients for each n, then that defines a function f hat of k, where k is n pi over L. So it means at the moment it's only defined on this discrete set of values of k, which is the purple lattice that I drew just up here. You see I drew minus 2 pi L, minus pi over L 0, and so on. That's this lattice in k space. K is going to be what we call the wave number. So when you looked at plane waves, you've seen the wave number of a plane wave. And this formula now should remind you of something like a plane wave, because we've got e to the ikx, okay? So we've got a sum of plane waves in space. We haven't got any time here or anything at the moment, but we're just looking at something in space, okay, in x space. So, okay, so the idea, there's a formula for a function, which is just a way of rewriting the Fourier series. So far I haven't actually done anything, but now I want to think about in the limit when that when we take L goes to infinity, then we're going to replace that by a sum, okay? But sorry, we're going to replace that sum by an integral, okay? So the idea is you should think of, so let's actually give it another color. Well, let's give this a formula like a purple star, okay? So so what you should do, you should think of that formula with the sum over k values. If you think of that as a Riemann sum, so consider the right-hand side of formula star as a Riemann sum. Riemann sum for, so what are we integrating? Well, when you have a Riemann sum, so the point is you take the width, so the width here is delta k, you take the width to go to 0, and then that sum in the limit should give you an integral, okay? So So what are we integrating? We're integrating 1 over 2 pi f hat of k. So e to the ikx and that's going to appear, so that arises from the limit and delta k goes to 0 and with L going to infinity. Okay, I don't want to say it. So because when L goes to infinity, then that sends delta k to 0. Okay, so this gives an integral formula. F. So what do we get? Maybe I should, I don't know, maybe I should do a different color. I like purple colors. I think that's too thick though. Hold on. It's going to be too fat. So let's make it like that. Okay. So what do we get? We get f of x is 1 over 2 pi. Okay, so you can't probably see it anymore, but it's this. Let me circle it with red now because I finished with it. So the formula that I'm trying to show you, let's put me over here. Sorry, not to get out of the way. So the formula that I'm trying to show you is formula star, which is this one. Okay, so we had a sum over k values, and k was a set of lattice points regularly spaced on the k axis, where the k values are on a lattice. But now we're still going across the whole k axis, but we're taking this gap between the points is going to 0. So what that becomes is an integral over the whole k axis. So that's going to be an integral. Let's put me back over here. That's going to be an integral from minus infinity to infinity. Okay. And then I've got f hat of k times e to the ikx, and then delta k becomes dk. Okay, so that's sort of how you go from a Riemann sum to a Riemann integral, but I'm not being really precise about this, all the conditions that we need to make this thing converge, but this is meant to be more of a kind of intuitive understanding of where the Fourier series, how the Fourier series, naturally leads you to think about the Fourier transform. So the point is that we've replaced a Fourier series for f by an integral, and the integral is over, it's e to the ikx multiplied by some function f hat of k. Okay, and f hat of k is sort of the analog of the Fourier coefficients. So the question is, there should be, this is the formula star up here. So what I want to do is go back to the formula for Cn, which was here. Okay, so now I want to look at this formula. So let me circle this one. Let me take color. Okay, so this formula here. I want to figure out what. Okay, so maybe my alpha, I didn't even need my alpha. I was trying to give myself some freedom, and I probably didn't need to use this freedom. It doesn't. So alpha, I don't think alpha is gonna matter. But let's see. Maybe I'm speaking through my hat. Okay. Okay. Well, let's see. So. Yeah, so the constant alpha, I've realized I was trying to make sure that the point of leaving alpha in there is that people define the Fourier series and the Fourier, well, especially Fourier transforms, they define them with different scalings. So sometimes here in this formula here that I've just written here, I've got a 1/2 pi, but actually different authors write this differently. So some people use 1/√2 pi. Some people don't put any 1/2 pi here. But then what we want to find is now a formula for f hat in terms of f. Okay. So let me kind of proceed with that, and then you'll see. So yeah, I could have used alpha to do some more scaling. Also, if you're a physicist and you do quantum mechanics, then you don't also necessarily want to scale by factors of √2 pi, but you also want to scale by h bar, which is Planck's constant over 2 pi and so on. So I'll also put in kind of constants with dimension can appear. And then in that case, in quantum mechanics, the wave number k will be replaced by the momentum variable in quantum mechanics. So that's a sort of another place where you often do a different scaling. Or if you're doing engineering, then you do Fourier transforms in time, and then the variable k will be the frequency. So depending on the context, there are different scalings. And I guess if you want to translate between these different formulae, you could use this alpha to rescale by different amounts. But at the end of the day, for what I'm doing here, I don't actually need it, but I was just sort of hedging my bets by leaving myself another constant. Okay. So yeah, I mean, that's the way that I work out most calculations, because I don't know the answer of what I'm trying to work out at the start. But in order to kind of figure the right answer, I leave myself some freedom, some extra leeway by putting in a constant, and then I can always fix up the constant at the end. Okay, so here I did that, but I think I could have left it out, and maybe it would have been simpler for you to understand, but I'm sorry about that. Okay, so what do we want to do? We want to now find a formula for f hat. So now f hat, okay, well, what is that? It's equal to alpha Cn times 2 pi over delta k. But what is delta k? Well, delta k is pi over L. Okay, so this is alpha Cn times 2 pi times, so this is going to be L over pi, okay, because we know what delta k is. So this is going to be 2L alpha Cn. Okay, so does that make sense with what we wanted to do? Great, excellent. So if you look at this formula gives us alpha Cn is 1 over 2L times an integral from minus L to L, okay? But remember that, so from above, alpha Cn is equal to 1 over 2L. Sorry. 1 over 2L, the integral from minus L to L of f of x. And then if you look at it, what we had, we had minus I n pi x over L, but that's just minus I kx, okay? And this is integrated with respect to x. So if we multiply through both sides by 2L, we get 2L alpha Cn is just given by this integral from minus L to L. So what that tells us is that f hat k is equal to the integral from minus L to L of f of x times e to the minus ikx dx. And then now, this was before we did any limits. So, taking L goes to infinity when delta k goes to 0. So now we can take L goes to infinity. And then what we end up with is now the formula for f hat as another integral across the whole real axis. So what we get is f hat of k is the integral from minus infinity to infinity of f of x e to the minus ikx dx. Okay, so this is actually where we wanted to get to today. And then let me get another color. Let me try and get red. Oops, I'm sorry, I lost it. Okay, so this thing here, I'm going to try and put that inside a red box. So this thing here is what's called the Fourier transform of the function f, function of x. So we have a function of x, and we do this integral against x, so an integral with respect to x. But inside the integral, there's a k appearing in the integrand. So that means that the answer is not just a number, it's a function of k. And so that's why then that function we call f hat of k. So that's the Fourier transform of f of x. It's a function of another variable k. So that's the Fourier transform. And then this formula above that we derived, which came from the Fourier series. Okay. Oops, sorry. I'm trying to get my boxes to look. So this is the inverse Fourier transform. Okay. So far this just looks all very abstract because we haven't used any specific functions. But I want you to sort of stare at those two formulae for a minute. So those are the main formulae that we're going to use. And what I've shown you is not really a rigorous justification for these formulae for why they work, but it's more of an intuitive justification, or it's more of an intuitive argument, say a heuristic argument for how these things arise if you think about start from periodic functions. So one thing is actually think about how does this even make sense? So one of the things that I mentioned already when I was drawing some squiggly graphs before, just now, I said that I wanted f of x to go to 0 at the endpoint, so at minus L and L. Well, if it was periodic, then it has to take the same value at both ends if it's really a function. But the reason that I want it to go to 0 is that here I'm integrating from minus infinity to infinity. And if you have an integral along the whole real axis, then there's a question of convergence. So we might, in the first place, typically would want f to be a bounded function for finite values of x. But then if this integral is going to converge, then we really would certainly require that the function f decays at infinity. Otherwise, if it doesn't go to 0 at plus or minus infinity, then the integral is not going to be defined. Okay, so that's a sort of basic condition that we want, but in fact we might require something more. So if you're used to thinking about Fourier series, then when you talk about convergence of series, you have absolute convergence of a series. It means the modulus of the sum of the modulus of the terms is convergent. And you can do the same things with integrals. So you would take the modulus of the integrand has to give you a finite value for the integral. So in this case, you've got e to the ikx and e to the minus kx appearing in these integrals. So when we integrate f of x and times e to the minus ikx, the modulus of that is just the modulus of f of x, because e to the minus ikx has modulus 1. So now one requirement that we want, so we want to normally a minimum requirement is that the integral of mod of f of x dx has got to be finite. Okay, so there's a way of saying that, which is what's called sort of LP spaces. So what you say is that f is in the space L1. Okay, so that's the set of all functions such that mod of f is integrable on the whole real axis. Okay, so that's a sort of notation for those functions that satisfy that condition. So that's also a vector space. You can think about it because if you take a linear combination of any two functions that satisfy that condition, and essentially the triangle inequality tells you that any linear combination belongs to that those functions whenever the original functions you started with do. So that's the basic requirement. But sometimes we put more conditions as well. And I'll maybe say we can talk about that maybe in the future. But just to sort of finish off, so we have this, just to sort of get a picture, so what we're doing. So we start with functions on X space, and then we do what's called the Fourier transform. And what we get is functions on K space. And the way that we denote this is that we take a function f. So I'll write f of x, but we could just write f. And then we're going to use a symbol for Fourier transform, which I'm going to call f, a curly f. Okay, so there's too many f's here, but this is a kind of calligraphic curly f. And so what we get is a new function called f hat of k. And I can also write that as curly f acting on the function f of x. Okay, so it's like the Fourier transform is like a function on functions. So when I say functions, really I need to be careful because, as I said, not any old function will work here. Not any old function of x will have a Fourier transform. So if I had a function that you can't integrate along the whole real axis, then that's not normally going to give you a Fourier transform. There are some strange, sort of unusual things that we're going to mention briefly later on, called distributions, which are not really functions, but sometimes we can also define Fourier transforms for more general things than functions. But typically we're thinking about functions, and they have to be functions which are decaying fast enough at infinity, at plus or minus infinity, so that this integral up here that defines the Fourier transform, this integral formula here, has to make sense. All right. So that's sort of one way around. And then we can also write and then draw another picture, because above we also had this other formula, and I've called that the inverse Fourier transform. So now what I want to do is sort of show you an arrow showing it going back the other way. So what I'll do is maybe take a different color. Maybe I'll take, I don't know, this kind of purple or something. So what I want to show you is another arrow going back the other way. So this is called the inverse. Fourier transform. Okay, so that and what that's doing, I should have made the arrows the same length, but never mind. So this is taking you from a function on k space, so a function of k, going back to give you a function on x space. All right, so that's going the opposite way. And again, so again, we sort of, if we started from a function of k, and this integral, it's basically the same kind of integral, except that I've got e to the ikx up here instead of e to the minus ikx, and then I've got a 1 over 2 pi. So there's a scaling. And as I was trying to say, and why I sort of maybe faffed around with having this extra constant alpha, is that there are different ways to define these two things. So according to how you scale everything. So it is possible to put, a scaling in so that the formula has, square root of 2 pi here, and also a square root of 2 pi on the bottom here, or other scalings are possible, okay, depending on, as I said, if you're doing quantum mechanics, you have other sometimes, or engineering, you might have physical constants as well that you want to stick into the scaling, okay. So that was why I was being a bit sort of cautious about what scaling I wanted to do, but I didn't really need to be. But we're just going to stick to this definition, okay? So then the point is that if you have your function f hat of k, and then you apply, so I'm going to put the arrow going back the opposite direction, the mapping is going, then this thing I can write as curly f inverse, so that's again like a function on functions, which is the inverse Fourier transform. And what that gives you is it gives you the function f of x back, and I can write that as f inverse acting on f hat of k. Okay, so that's the overall process of what Fourier transforms do in a very kind of schematic and heuristic way of deriving them from Fourier series. And what we need to do next then is to start looking at some examples of particular functions calculating Fourier transforms. Okay, so that's a good place to stop.